This is what it looks like when AI learns. A landscape with millions of dimensions, cliffs, valleys, saddle points. Two models, trained independently, land in completely different valleys. And yet, a secret tunnel connects them. This is the world of lost landscapes. In episode 2, we learned about gradient descent, rolling a ball downhill to find the minimum. But today's question is different. What does that hill actually look like? With one parameter, the loss function draws a simple curve. Valleys are good predictions, peaks are bad ones. The ball rolls down to a valley, a local minimum. But real neural networks have millions of parameters. Even with just two, we get a three-dimensional surface. What was a curve becomes a landscape. The key to understanding this shape is the Hessian matrix, the matrix of second derivatives. Its eigenvalues tell us the curvature in each direction. When all eigenvalues are positive, every direction curves upward, a valley. When all are negative, a peak. But when signs are mixed, we get something fascinating, a saddle point. Along the x direction, eigenvalue +2, it curves up like a valley. But along the y direction, eigenvalue -2, it curves down like a hill. This shape will turn out to be far more important than any local minimum. Here's a common misconception about training neural networks, that the main problem is getting stuck in local minima. The truth is far more surprising. For a critical point to be a local minimum, every single eigenvalue of the Hessian must be positive. Heuristically, think of each eigenvalue sign as an independent coin flip. What are the odds that all coins land heads? With one dimension, 1 in 2, two dimensions, 1 in 4, 10 dimensions, approximately 1 in 1,000, 100 dimensions, 1 in 10 to the power 30, and a typical deep neural network has 1,000,000 parameters. The probability of a local minimum is approximately 10 to the -300,000, essentially zero. In high dimensions, almost all critical points where the gradient vanishes are saddle points, not minima. So if gradient descent encounters a saddle point, the gradient is nearly zero, and the algorithm stalls. But stochastic gradient descent has a secret weapon, noise. Mini-batch gradients aren't exact, they have random fluctuations. And when those fluctuations happen to point along a direction of negative curvature, they get exponentially amplified, naturally pushing the model away from the saddle. Watch, the noise gives just enough of a push in the escape direction. In 2014, Dauphin and colleagues showed this experimentally. Standard SGD stalled at a loss of about 1.0 near saddle points. Their saddle-free Newton method escaped, reaching a loss of 0.57. The good news, for modern deep networks, SGD's built-in noise is usually enough to escape saddle points on its own. In 2018, a team of researchers found a way to actually see what these landscapes look like. They took a trained network, picked two random directions in parameter space, and plotted the loss along that slice. The result was one of the most striking images in all of deep learning. On the left, ResNet 56, a network with skip connections. Its lost landscape is a smooth, gentle bowl. On the right, the exact same architecture but with skip connections removed. The landscape becomes chaotic, jagged, full of sharp features. The smooth landscape achieved 5.89% test error. The chaotic one, 13.31%. That's a 7.42 percentage point gap, caused entirely by removing skip connections. So why do skip connections make such a dramatic difference? A residual block computes y equals f of x plus x. The f of x part learns the residual, and the plus x is the identity shortcut, a direct highway for information. When we compute gradients, the chain rule gives us this beautiful decomposition. The gradient of the loss with respect to x includes an identity matrix term. This plus y is the gradient highway. Even if the learned function f has tiny gradients, the identity term guarantees that gradients can never completely vanish. Before ResNets, deeper networks actually performed worse. A 34-layer plane network had higher error than an 18-layer one. ResNet fixed this completely. He and colleagues pushed all the way to 152 layers, winning the 2015 ImageNet competition with just 3.57% top 5 error. Here's one of the most surprising discoveries in deep learning. Imagine training the same neural network twice, with different random seeds. Each run converges to a different solution, landing in a different valley of the lost landscape. Now, what happens if we draw a straight line between these two solutions and measure the loss along the way? Disaster. For VGG16 on CIFAR 10, the midpoint of the straight line has 90% test error. That's worse than random guessing. But watch what happens when we use a curved path instead. A quadratic Bezier curve that bends through a low-loss region. The maximum error along this curve, just 7.01%, almost identical to the endpoints, from 90% to 7%, just by changing the shape of the curve connecting two solutions. Two independent teams discovered this in 2018. Garipov and colleagues at New York University found these Bezier curve connections. Draxler and colleagues at Heidelberg found that for deep networks, the error increase along connecting paths is just 0.2 to 0.5 percentage points. The implication is profound. The loss landscape is far more connected than anyone had previously believed. What looks like separate valleys are actually connected by hidden low-loss tunnels. Before we learn how to shape the landscape, we need to understand the most fundamental problem in machine learning: overfitting. Imagine we have 10 data points sampled from a sine curve with some noise. Our goal? Find a polynomial that captures the true pattern. A degree 0 polynomial is just a flat line. It captures nothing. This is underfitting. Degree 1 gives us a straight line. Better, but still not enough. Degree 3. Now we're capturing the sinusoidal shape. This is close to optimal. But what about degree 9? With 9 degrees of freedom and only 10 data points, the polynomial passes through every single point. Training error, essentially 0. But look at how wildly it oscillates between the points. This is overfitting. The model has memorized the noise, and the coefficients? They explode to hundreds of thousands, enormous numbers fighting each other just to thread through 10 data points. This is captured by one of the most important equations in machine learning, the bias-variance decomposition. The expected error of any model can be split into 3 terms: bias squared, the error from oversimplifying; high for flat lines, low for complex models; variance, the error from being too sensitive to the specific training data; low for simple models, high for complex ones. The total error is a U-shaped curve. Too simple, and bias dominates. Too complex, and variance explodes. The sweet spot is somewhere in the middle. In the next sections, we'll see 3 powerful ways to fight overfitting: regularization, dropout, and good architecture design. Each of them reshapes the loss landscape to make it easier to find that sweet spot. How do we prevent overfitting? The most elegant solution is regularization, and its geometry is beautiful. L2 regularization, also called ridge, adds the squared magnitude of the weights to the loss. This creates a circular constraint region. The optimizer must find the lowest loss that stays inside this circle. When the loss contours touch the circle, they meet at a smooth point. Both coordinates are non-zero. L1 regularization, called lasso, adds the absolute values instead. This creates a diamond-shaped constraint region. And here's the magic. When the contours touch the diamond, they almost always hit a corner. At a corner, one coordinate is exactly 0. This is sparsity. L1 automatically selects which parameters matter and sets the rest to exactly 0. To see why, a vector on the axis like 1, 0 has L1 norm of 1, but a vector at 45 degrees with the same length has L1 norm of root 2, about 1.414. L1 genuinely prefers sparse solutions. There's a deeper connection here, one that links back to episode 3 on Bayes' theorem. L2 regularization is mathematically equivalent to placing a Gaussian prior on the weights. The bell-shaped curve gently discourages large values, but never forces them to 0. L1 regularization corresponds to a Laplace prior. That sharp peak at 0 actively pushes weights toward exactly 0. Regularization is just choosing a prior. It's Bayes in disguise. What we learned about beliefs and evidence in episode 3 is exactly what's shaping the loss landscape right here. The second weapon against overfitting is dropout, and the idea is beautifully simple. Here's a neural network with 4 hidden neurons. During each training step, we randomly turn off some neurons. Probability of keeping each one, 50%. Next step, a different random mask. And again, and again. Each mask creates a different subnetwork. With 4 neurons, there are 2 to the 4th equals 16 possible subnetworks. Scale that to just 10 neurons, and you get 1,024 subnetworks. At test time, we use all neurons but scale the weights by the keep probability p. This approximates averaging overall subnetworks in a single forward pass. The results are dramatic. On SciFar 100, dropout reduced the error from 43.5% to 37.2%. There's one more technique that reshapes the loss landscape: batch normalization. It normalizes activations within each mini-batch, then applies a learnable scale and shift. The original paper claimed it works by reducing internal covariate shift, but Santerkar and colleagues showed in 2018 that this explanation is wrong. The true mechanism is landscape smoothing. Batch norm improves the gradient smoothness by roughly 4 to 6 times. Gradients become more predictive, allowing larger learning rates and faster convergence. This is the core theme of this entire episode. Architecture choices reshape the terrain itself. Skip connections, batch normalization, regularization, dropout. All of them sculpt the landscape into something the optimizer can navigate. And one more beautiful connection. Gal and Garamani showed that dropout is mathematically equivalent to approximate Bayesian inference. Keeping dropout on at test time gives you uncertainty estimates for free. Another link back to episode 3. Let's step back and see what we've discovered about the hidden terrain where AI trains. First, loss functions don't just give us a number. They create a landscape, a vast terrain over the space of all possible parameters. Second, in high dimensions, the critical points of this landscape are overwhelmingly saddle points, not local minima. The probability of a true local minimum is essentially zero for modern networks. Third, architecture matters. Skip connections transform a chaotic, untrainable landscape into a smooth bowl that any optimizer can navigate. And fourth, regularization and dropout don't just prevent overfitting. They sculpt the landscape itself into healthier shapes. Our mathematical toolkit keeps growing. In episode 1, we learned that AI speaks the language of vectors and matrices. Episode 2 taught us how gradient descent navigates the terrain. Episode 3 showed how Bayes' theorem handles uncertainty. Episode 4 revealed backpropagation, the algorithm that teaches machines. Episode 5 gave us softmax and cross-entropy, the tools of decision-making. Episode 6 proved that neural networks can learn almost anything. And today we explored the landscape they learn on. Next time, convolution, the mathematical operation that gave AI the ability to see. Thanks for watching.